and Abir Altada.
Yes.
Thank you very much.
Thank you so much, sir.
Good afternoon, everyone. So my name is Vahid. I'm currently working as a senior structure advisor at SCS National Highways, and I previously worked as a future road fellows at Cambridge University. So today I will just give an overview about my research on the freeze-thaw performance of low carbon self-filling concrete pavements incorporating superabsorbent polymer. So in this presentation, I will briefly introduce the problem statement, the research background, and the motivation behind of this research. And I will then discuss the key findings of the experimental program and the key findings in terms of the compressive strengths, the freeze-thaw resistance, and some microscopic observation, and followed by the key takeaways of this presentation. So when considering the current challenges of our road infrastructures, I think the decarbonizing of concrete assets and extending the service life of our infrastructures are key priorities for organizations worldwide. To put it in the context, I would like to highlight some key facts and figures. For example, National Highways manage 4,300 miles of roads, over 20,000 of structures, 12 road tunnels, as well as the drainage, earthworks, and technology equipment. And the emissions coming from the constructions and maintenance of our networks is around of 734,000 tons of CO2 equivalent during 2020. And out of that, 27% of that emissions was from the constructions and maintenance related to the cement and concrete. And furthermore, Portland cement concrete accounts for about 7 to 8% of the CO2 emissions into the environment. National Highways also has the concrete pavements, which are representing approximately about 4% of the strategic road networks, and they are mostly old concrete pavement, jointed concrete pavement with some sections of continuously reinforced concrete pavement. As you can see at the bottom row images, there are a lot of problems related to the deteriorations and the agings because of exposure to the XF4 or XD3 related to the corrosion and the freeze-thaw exposures. So that's the motivation to conduct this research, and I will explore how we can develop self-filling concrete pavements, which is also low carbon concrete materials to address these challenges. So with the growing demands of smart and resilient infrastructures, I think we can adopt a biomimetic approach via the self-filling concrete technology, which can extend the service life of our infrastructures, reduce the maintenance costs, and perhaps lower the both capital and operational carbon. So although there are like a lot of promising results in terms of using self-filling technologies across the various applications, to date there has been limited research in terms of developing an effective smart self-filling systems for concrete pavements. So in this study, I have considered the use of superabsorbent polymers to see how it would impact the freeze-thaw performance of the concrete. So what is superabsorbent polymers and how does it work? So superabsorbent polymers are natural or synthetic three-dimensional cross-linked polymers, which they can absorb. They have a high capacity of absorptions of the water and the fluid. So they can, in the dry state, you can see the chematics mechanism of the SAPs. So in the dry state, they absorb the molecules of the water and they become salts. And then after in the internal curings, they release that absorbed waters and they leave behind some macropores, which resemble the air entraining agent systems into the concrete, which are favorable for freeze-thaw performance. On the right-hand side, you can see a quick experiment showing that how dry state superabsorbent polymers absorb the water within 5 minutes and they have been in the solid state. And at the bottom row images, you can also see some microscopic images of the SCMs with irregular shapes. So roller compacted concrete, or called RCC, they have been introduced in the UK in 2002, and thereafter they have been incorporated in the highway specifications. So again, the results shows that there are some initial cost saving in the range of 10 to 50% compared to traditional modes of concrete pavements. But the thing is that most of the concrete pavements are still based on using of 100% of Portland cement, and based on the current state of our specification, the maximum percentage of the GGBS and even fly ash that could be used in our concrete pavement is limited to 35%. So one motivation behind of this study was that whether we can go beyond that and use a higher percentage of the supplementary cementitious materials into the concrete pavement. So in terms of the experimental program and the material that have been used in this study, Portland cement SEM1 and again the slag supplied by Hansen has been used as a cementitious material. Sharp sand and gravel with the maximum aggregate size of 2 and 11 millimeters has been used as a aggregate. I have used the tap water for the mixing of the concrete, and SAP BASF with particle size of 100 micrometers has been used as a self-healing additives. And finally, Secomen 700 was used as a super plasticizers and water reducing agents into the concrete mixers. I developed 8 different concrete mixes in this study in 2 groups of standard and roller compacted concrete. In each group of mixes, I have a reference concrete with 100% of Portland cement. The second mix is the one that 50% of Portland cement has been replaced with GGBS to consider the effect of low carbon materials. The third mix is the one that 0.3% of superabsorbent polymers has been used to develop SAP-modified concrete. And the final mix is a combination of having 50% slag aligned with 0.3% of superabsorbent polymers. As you can see, the water boiler ratio in all mixes has been constant in the value of 0.4 to 5. And due to the measured performance and the capacity of the water absorption capacity of the superabsorbent polymers, I have slightly modified the water content in the SAP modified concrete mixes to ensure that the effective water boiler ratio remain constant. And also in terms of the experimental program, I measured the compressive strength from 1 day to 91 days and the freeze-thaw resistance at each 7 cycles up to 98 cycles for freeze-thaw resistance without de-icing cells and 56 cycles with de-icing cells. This slide shows the freeze-thaw test method that has been adopted in this study according to the BSI standard. And you can see the sample preparation, which I have used concrete disc with the dimensions of 100 by 50 millimeters. And then I put the samples in the plastic tubes, which are insulated with the polyester. And then I put the samples in the freezing chamber. They are subjected to temperature reductions from 20 degrees of Celsius to -19, and then returning back to 20 degrees of Celsius. For freeze-thaw cycles, freeze-thaw resistance without de-icing cells, I used the 3 millimeter of deionized water on the top of the specimens, and I used ultrasonic pulse transmission time to measure the relative dynamic modulus of elasticity. And for freeze-thaw resistance with de-icing salt, I used the same method of sample preparation, but I used 3% sodium chloride solutions as a medium on the top of the samples, and then I collected and filtered and weighted the mass of scale material on the surface of the concrete. So this slide shows the results in terms of the compressive strength development over the times. As you can see, the best performance was achieved in both group of mixes in reference concrete, which 100% of Portland cement has been used. By replacing a proportion of that with GGBS, we have seen a strength reduction in all concrete mixes. And when I have used superabsorbent polymers, since I have used an additional water to compromise for consistency of the concrete, you can see that there is also a reduction in the compressive strength of the concrete. And the worst performance was achieved when we have both combined use of SAPs and GGBS in concrete. In terms of the freeze-thaw resistance without de-icing salt, you can see that by increasing the number of the freeze-thaw cycles, we have a reductions in the internal stiffness of the concrete because of introductions of the microcracks inside of the concrete. Again, the worst performance was achieved in the reference concrete, while with the addition of SAPs or replacements of Portland cement with GGBS, we have seen an improvement in terms of the performance of the concrete. And this slide also shows the durability factor of concrete samples. As you can see, again, based on the standard, all the concrete samples developed in this study meet the requirements of achieving more than 90% of the durability factor. This slide shows the freeze-thaw performance with mass scaling. Again, by increasing the number of freeze-thaw cycles, the weight of scaled material has been increased as expected. But the worst performing here is the mix with 100% of Portland cement, and the use of GGBS was very effective in terms of improving the performance of the concrete. The effect of superabsorbent polymer was slightly different in standard concrete mixes and roller compacted concrete mixes. And it has negligible impact in RCC mixes. And the best performance again was achieved in the mixes that we had used both materials at the same time. And this slide visualizes the surface deteriorations in two groups of mixes, including roller compacted reference concrete mixes and standard lower carbon concrete self-filling mixes. As you can see in roller compacted concrete, the deterioration has been moved from the cement paste to detachment of the aggregate, while in the standard concrete mixes, it has been mainly limited to cement paste deteriorations. And finally, this slide showing some microscopic observations. So it shows that the positive impact of using GGBS in terms of improving the interfacial transition zones of the aggregate and this bonding between the cement and aggregate. And at the bottom right-hand side images, you can see that by inclusion of superabsorbent polymer, we have some air voids that negatively impacted the compressive strength and some other performances. Here are some key takeaways from this presentation. So regardless of the concrete pavement, the replacements of Portland cement with 50% of GGBS, the addition of 0.3% of SAP, it was resulted in a reduction in the concrete compressive strength. All developed concrete mixes demonstrated excellent freeze-thaw durability factors, which are more than 90%, despite a slightly higher internal damage in RCC mixes. RCC mixes shows marginally higher de-icing salt scaling, while extended water curing effectively reduced the surface carbonation in lower carbon concrete. SAP addition improved salt scaling resistance in conventional concrete, but had limited influence on the RCC performance. And finally, GGBS enhanced the ITZ quality, whereas SAP's incorporation led to a less compact ITZ due to additional water intake. An acknowledgement to the Horizon European for funding this project, and I would be happy to answer any question. Thank you.
Questions?
Just for my knowledge, could you please explain SAP a little bit more for us? So it's a polymer that it absorbs the water and the materials, and it goes into the pores and expands.
It's a type of the polymer, so it is a type three-dimensional polymers, and when it absorbs the water at the dry state, it's very tiny materials, but when it absorbs the water, it becomes soil. But again, during the internal curing and over the age of the concrete, it releases the water that has been already uptaken and leave behind some macropores. So it is quite similar to the work, to the way that we are adding air entraining agent to the system. So we are introducing some uniformly distributed air voids into the concrete system, which are favorable for the freeze-thaw performance because there are some space for the water to go through. And then when it's in the freezing stage, it has some space to swell on that stage. Otherwise, there were some internal stress inside the concrete, which resulted in a deterioration of the concrete.
That makes sense. So I was thinking, why do you want to make
some voids into the concrete?
Yeah, because then that would.
It depends on the level of the voids. Because, for example, if you are exceeding some level of the voids inside the concrete, it shows that it has also some negative impacts in the concrete. So we have to be careful in terms of how much SAPs we are adding into the concrete.
And so you have more porosity in the material, and so it is good for
some application.
For regular concrete, they have problem with the reinforcement.
Yeah. I have also done some another research regarding the decarbonation or RCPT test, the corrosion resistance of the materials, and those air voids are not favorable for those durability indications.
Makes sense. Yes.
In terms of cost, how are they different?
Cost.
Because I didn't hear, but I think in practical will be used